Let's start first of all, just before I get into anything else, I guess today you have your homework, one is due. How many people have sort of got made at least a pass through every part of the assignment? Okay, signs of life. Okay. Has anybody tried to submit it to Google Classroom? And what happened? Oh, nothing. I mean, it worked. Okay, so that's reassuring. Okay, I recommend that people do this. Don't wait till 11:59 to do this. There could be all kinds of problems. And if you have problems, the Piazza is a good way to make sure that you get that. Before I go any more into other stuff, are there any questions or discussions or observations about the assignment due today? Have we talked through that pretty quickly? Any questions or concerns? Yes.
In question number 2, the n, if we select an n, then can we change it later?
Yes, so why did I have you select an N? Okay, the main reason was a fear that some of you were using came here with your grandfather's computer that he bought back in 1956, and you ran it, and you said, oh, I can only compute a matrix that's 10 by 10 or something like this. Okay, so I didn't want somebody to balk and have trouble doing it. Did anybody, out of curiosity, who here was able to compute the correlation coefficient on the time series between all 500 and all 500 stocks? And how long did that take?
About
2, 3, or 4 seconds. And when did you buy your computer?
a month ago.
Okay, a month ago. Okay, so that is a proof that maybe my concerns were unfounded if you have a modern computer. But so that was the main reason why I ask it. So if you do something, you use this on your, it therefore may make sense though to use a different number of companies on different types of analyses. That's, I guess, what your question is. And if it makes sense, do it that way. Okay, yeah.
For question 2, is there a number you want us to pick, like a slot, like 100?
Well, what did I hope? Okay, actually, it's funny. Today's the day I didn't, unfortunately, I couldn't find the homework, the assignment paper. But what I believe, what I would have wanted was, in general, I would have loved to see you do 500 by 500, okay? And that be the one that you are normally working with. Now, I'm going to guess when you did that, there might be some problems with things like visualization.
Yes.
Okay? And you're saying, oh, I can't see 500 by 500 numbers.
I can't see one. I tried one, I was like 40 by 40, and ever since.
Okay, so one question, the question of, oh, I can't see 40 by 40. Okay? So part of me says, yeah, you can't see 40 by 40. And part of me says that if you view it, if you represent the thing right, you can see and learn from it a lot more than you think. Okay? That's kind of my first observation. So when you did it, tell me something. Did anybody draw that matrix so it was in colors? And what did you see when you saw colors? Did you see flashing colors all kinds of places?
You see the red line of the ones that were the same ones, and then you see all the different colors. The main issue I ran into, the numbers would overlap, so it looked like binary after a while.
Okay, so what am I hearing here? Okay, I'm hearing, yes, you should have a strong main diagonal because one should be 1. Okay, I'm hearing you said that the numbers don't fit when it's too small. Well, that's undoubtedly true. One of the great things about color scales is that that numbers don't have to necessarily appear there. Okay? this is just for, again, we're going to talk about visualization in coming weeks. One of my things I kind of hope is that you find that certain things that seemed like they were really dumb turn out to be harder than you thought, okay? And that way you have more respect when we talk about the subject in here. That's part of my thinking on this. But yeah, so colors might make a difference. Anything else that might make a difference to make that view nicely? Did anybody draw it in colors? Okay, and what did you see when you drew it in colors?
I mean, it was the same things we already mentioned. It's just strong diagonal, and then like all the high correlation moves are obviously like deeper or like higher color value, so a stronger, deeper value, something like that.
And did you see patterns there, or did you just see a mix of light and dark colors?
I'm looking at it right now. I don't see many patterns. It's just like a couple of mixtures of red and dark.
Couple of what? Okay, so you're saying that the interesting thing was when there are patches that are all dark or something like that. Now, did you do anything to make those patches bigger?
I just made the whole plot bigger so I can do 50 by 50 or like 100 by 100.
Okay. Now, do you have any control of anything on this plot otherwise? Okay. You tell me you can color it. Is there any other control you have over this thing? Yeah? You can order the columns. Okay? Is there a logical order for the columns that might make something revealed? Okay, yeah?
Maybe you were ranking in part 2, actually.
Maybe you're ranking by, so if it is the case that companies by importance, let's say, behave similarly, that if it's a good day in the market, important companies do well and unimportant companies do less well, then that's what you should see, something like that, if you lay them out by importance, right? Is that the way the market performs? I don't know. Yeah?
So I think if you use Seaboard, there's like a cluster map, and basically what that does is that it orders the columns and rows hierarchically. So basically what it tries to do is that it tries to take like the companies that are the most closely related together, and it tries to like group them, group their rows like next to each other, so they can build like a hierarchy, and it shows like sort of a hierarchy.
Okay, so what you're saying is that there is some magic function there that orders the columns explicitly by similarity, right? And that if you order it by similarity, you will probably get patchy regions, right? And is that what happened?
Yeah. So
And was the ordering of the companies kind of interesting?
yeah, so I found that a lot of the banks, right, they tended to be clustered together.
Okay, so what you're saying is that if you order that one way to see more structure here might be to permute the columns. And you're saying you think the banks all performed away. Because again, it kind of, does it make sense that on days that are good for one bank, it's good for the other bank? Maybe interest rates going up is good for a bank. I think that's true, but I'm not 100% sure. Maybe a financial crisis is bad for banks. Is that true? Probably. Okay. So again, thinking about it, you're right. There's too much data there for you to see if you just display a matrix of dots, okay, or a matrix of numbers. But there are ways to see things that are revealing. And if you have time, play with that. If you don't have time, do what you can, but get it in comfortably before midnight. Any other questions about the assignment? Did anybody, again, I dropped some kind of a hint last class about the regression stuff. Did anybody listen to my hint and try to do something with it? Did it do anything? He says it did something, son of a gun. Okay? So think about this, because again, it's one of the things that I want to come out in this class, is that it pays to think about what your data is and understanding what your domain is, and thinking about whether or not it might, what you're trying to do makes sense to do, okay? And that's one of the things, that's kind of one of the intuitions I hope that people will come out in here, okay? Any questions about that? Actually, I'm curious about one other thing from that. If somebody tried a nonlinear classifier on the original problem, what you were trying to do before, I'm curious how much it recovers. Something like if you use a support vector machine. Again, what happened? You had a terrible result? You transform your problem a little bit, suddenly you have a great result, right? Now, I'm curious whether or not if you used a nonlinear classifier like a support vector machine or something like that, you end up getting better on the original problem. Okay, that should be an easy test for someone to run. Well, I talked about a transformed variable. And I'm going to say, if you want to know what I said, I guess it's on the recording, right? So you can think about that if you weren't here last time. Okay, yeah.
Well, I know I did it on a random forest with just the normal features, and it got like a pretty high R squared 0.97.
Okay, so with what you call it. So he's saying he did a random forest, which is a nonlinear thing, which we will talk about later. Okay, so he did very well. Do you have the original variable, the target variable, in among your features?
Oh, no, I don't have EPS.
Okay. Okay, let's say that, yes, maybe.
There's also like a caveat with, I think like with the net income, because the net income is basically just the EPS times the outstanding shares, right?
Yeah.
So if you include the net income, I found that your model can sort of end up cheating because, net income is just EPS times outstanding shares, right? So, like, don't you have to like remove some certain?
Okay, for now, do what you can. Again, we're exploring. I don't, do what you can and not what you can't, and what makes sense to you and what doesn't make sense to you, and get it in before midnight. Any other questions about the assignment? Okay, good. Okay, after the assignment, your next mission in life is to worry about the midterm. Yeah, question.
So a lot of the questions have like a subjective answer, like something that you choose that might not be appropriate according to the grading system. So is it like that, or as long as we justify the choice that we?
Well, what your job is to do the paper. Our job is to grade the paper. Okay, and we'll see what happens. Life is subjective, right? And there will be opinions based on what people do and don't do. Don't panic about that, right? We're going to curve. We're going to deal with it. Half of you are going to finish below the median. Half of you are going to finish above the median, and that's life. Okay? Any questions? Yes.
The question number 3, what does 140 mean?
What does 140 mean? Okay. Well, okay. I mean, I was going to say it could be 2 times 70, but what does it mean there? I am told, okay, word on the street tells me. I said there were about 140 splits, right? About means approximate, right? There seem to be weird things that are happening here. That are some things that I'm a little surprised seem to have happened, like some splits that almost didn't really change the value by very much. Okay? Do the best you can, and some people have come in and said, I found 40,000 splits. What am I supposed to do? Do I print them all? And the answer, if you found 40,000 splits, you're doing it wrong, right? Some people are telling me, I found 130 splits. Is 130 about 140? Maybe, about, roughly, kinda, okay? At least you're in the right area here, and that's a better sign of life, right? Any questions? Okay, good. So, next step for you in your life is the midterm. And for the midterm, it's going to be a week from today, Okay, again, there was a typo in my original early slide, and some people pounced on it, but do not bounce on it. It is a week from today, okay? The class is fuller. I tend to get very good attendance on the day of exams, okay? So in order to give people more room, I am going to ask people to break down into rooms based on what your Stony Brook ID number is. Who here has a Stony Brook ID number? Who here doesn't have a Stony Brook ID number? Okay, you all have a Stony Brook ID number. Okay, look at the first 3 digits of your Stony Brook ID number. If the first 3 digits are 115 or less, you're going to go up to Fry Hall 309 and take it. Okay? If your ID number is 116 or greater, the first 3 digits, you will stay here. Okay? Who here is taking the exam in Fry Hall? Okay? Who here is taking it here? Okay, it should be about a 1/3, ish split. Okay, and that will hopefully leave enough room for people to be comfortable here. Okay, any questions about the time or place? Now, how do you study it? Okay, first, I have posted a final exam. I haven't given a midterm in this class before. This year, you guys are an experiment. But I did post an old final exam on my web page, which you can get by clicking here, or go to my course page, okay? Or I will presumably put a better pointer to it on Piazza. The midterm is going to be on material that we will have covered up to the day of the midterm, so this class and the next class are included. It seems to be the chapters 1 through 5 in this book, okay? If you look at the book, at the end of every chapter, there are a collection of homework problems. What is the best way to study for the exam? I encourage you to read through the notes. I encourage you to read through the book, okay? But I strongly encourage you to try to work your way through the homework problems, okay, in each chapter. And I think you'll get a deeper understanding of what it does. Sometimes I include problems from the homework, from the book in there. I don't promise, and I maybe been backing away from that in recent years, but I reserve the right to. But I do think in good conscience that's a good way to do it. The problems I like to give, okay, are, hard in the sense of that there's some thinking involved, okay? Hard in the sense that there is hopefully a clear single answer, okay, or in general, okay? I'm going to try to avoid questions that, are more mushy, okay? But still, they're going to involve some thinking about what's going on. You're not allowed to use a calculator or a watch or any of the, a hyper-powered watch. One that tells time is fine, but one that does complicated things, no. You're not allowed books or notes, okay? Anything that's in the book readings or the lecture notes is fair game, okay? Any questions about that? Yes?
Are you saying, so with the book readings and lecture notes, are we allowed to take all notes, or we have to just use them?
No, you're not. No, you're not allowed to bring anything in here,
okay,
except except a pencil. Okay, so don't bring your notes. You can do. Of course, I don't discourage you from writing on a sheet of paper and keeping your own notes when you study, but those are for you and not in here. So there are no books, I should also say no notes. No calculators, no books, no notes are allowed. Okay? Any questions about that? Yes?
What is like the format of the exam?
Well, this is where looking at the looking at the final is probably a good idea. Now recognize that the final exam, the old final I posted, is for a whole course. So a lot of the stuff we haven't covered yet, right? I'm not going to ask you stuff we haven't covered yet. But what I look for, you look at it, you'll see it is kind of short answer kind of problems. Ideally, there are 2 problems printed per page, and there's room for you to write your stuff in, and you have to write the answer in that block that's half a page minus the length of the problem.
Can we assume approximately half of the final exam, like in length?
We can assume you're going to be done you're going to start at 9:30 and end at 10:50. And yes, I understand. So it's going to be half-ish the number of problems, okay? I don't know if it's going to be 6, I don't know if it's going to be 8, okay? It'll depend upon my mood when we deal with it, okay? Any questions? Okay, any other questions about the exam? The final other thing is that I did last year that I liked is, I am going to make up exams. I have some good and interesting questions that I'm going to put on it. But last year I asked students if they would send me questions that they thought might be good for the exam. What's a good thing if you mail me a question that would be good that you think is good for the exam and I think it's good for the exam? Is there any benefit to you for doing that? Yeah?
3 points for you on the exam if you know the answer.
Hopefully you know the answer, right? Okay? If you say, well, I don't know the answer, but the problem sounded interesting. I want to find the answer when I get the grade after, the answer key at the end. That's also an idea. But if you have some people kind of in the course of studying and looking at problems found some problems. If you want, email me them. If you don't want, don't email me them. I don't expect to get an infinite number of these things. And anyway, that's for there. Any other questions about the midterm? Okay, fair enough. So what I'd like to now do is finish up the section on ranking algorithms. Last class we talked about ELO rankings, okay? And just to review to make sure people understand the basic scheme. You're trying to rank players, teams, entities, students, okay, political candidates, whatever it is, by giving each one a score such that a higher score is better. But more than that, the scores can be used to kind of predict what the outcomes of matches are. So everybody started out with the same score. There is a formula adjusting it. Your new score after a match is going to be some constant k times the score that you actually got, meaning a win or a loss, okay, or perhaps a tie, minus the expected score that you should have gotten from the match based on the scoring differences. If the scoring differences were right, if it said that I should thump you, okay, and I in fact thumped you, okay, then my rating is probably about right and it shouldn't be adjusted. If my score said that I should thump you, and in fact you beat me, then I should lose points. And if you expected to be thumped, okay, and you won, you should gain points, okay? So basically this parameter K modulates the maximum point swing, how many points one party takes away from the other. And the expected score for a match was the score for a win times the probability that A wins, plus minus 1, the score for a loss times the probability A loses, which is 1 minus that. And so to complete the thing, all we need to know is what's the probability that A beats B as a function of the scores. This got us into a logit function. The logit function was what took a probability, a value, and mapped it to a probability, a number between 0 and 1, And our function has the nice property that if the difference is 0, the probability that I beat you is a half. If the distance is incredibly big, positive, probability I beat you is 1. And if the probability is incredibly negative, the probability I beat you is 0. Okay? Do you see how you can turn the score difference into a probability? And that's basically the system. Okay, and here was just an example I didn't look at in chess. Suppose I played Garry Kasparov in chess. I'm not a very good chess player, but somehow I beat him. If K was 40, I could take as many as 80 points from him, and that's what I did, and he got dropped by 80 points. He regretted he ever took a chance on playing me. Judith Polgar was the greatest woman chess player ever. Magnus Carlsen is the current champion, or if not either the current champion or the soon-to-resign current champion. Okay? If Judith and Magnus were playing each other, if Judith won, it would not have been a miracle because she's very good, but she took a certain number of points from him. Okay? And so her score got higher, his score got lower. If I then played her, it would be a miracle for me to win. I got crushed. My score stayed unchanged. Her score stayed essentially unchanged. I mean, in lower order digits, there's going to be a change. Any questions about the ELO rankings, why they are useful, why they are interesting? Yeah?
Is a property of this that the score basically just transfers? So you're not going to...
You're saying, is the possibility the score transfers? It's exactly that the score transfers. I am taking points. If I get points, I'm taking them from you. If we think back to that guy living in the prison, there was the murderer who wanted to get a high ELO ranking. He was taking it from fellow prisoners, okay? And the fellow prisoners had really low ELO rankings, but that didn't hurt their chances of getting clemency or anything like that, so they probably didn't care too much. Yes?
How do we start?
What?
We say nobody has no rankings. If we don't have any ratings the same to any person, how do we solve the goal start?
Say that one more time. I didn't quite hear that.
How do we start assigning ratings to?
How do you start? Well, everybody needs to start with a certain number of points. Okay? So everybody starts with a number of points, and their scores go, if they win, do better than expected, they will start accumulating points. If not, they'll just give their points to other people. Okay? That's kind of what happens.
So let's say the value is the starting value is 0 and then...
So the starting value, probably you don't like 0 because aesthetically then 0, you lose your first match, your point is negative. I believe, does anyone know what the starting value in chess is? For some reason, I think it's like 800.
Well, yeah, 800 or 1,000.
So they start people at like 800 or 1,000, okay, for paying admission. And then the assumption is you're playing against not so good players at first, so you have a chance still to get more points by playing against a weaker crowd. You get stronger and stronger, you'll probably play against stronger people. And that's kind of how it is. There's a limit. In principle, it's hard. You have to play an awful lot of games to get a high score playing lousy people, because you're going to be taking very, very few points from them. That's the argument that you want to play a higher competition, which is what you would like to see happen in chess. Any questions? Yes?
Can you explain the probability part of it?
The probability part. Okay, let me just try one. Okay, first, the most important thing to know is what the what the logit function is, because we will see this. Okay, the logit is this formula as a function of the score difference. Z is the score difference. If two players have the same score, what's the difference in their scores? 0. So Z would be 0. If Z was 0, e to the minus 0 is what? 1. 1 over 1 plus 1 is a half. If Z is very positive, what's going to happen? e to the minus something very positive is something very small. It's going to go to 1. If z was negative, it's going to go to 1 over infinity. Okay? So this always comes to a number between 0 and 1. It has this shape where if the differences are close to 0, there's a healthy probability for both sides. Once you get a big difference, though, it's really, the probabilities get very close to the extreme values. Okay? Any questions? Which is what we kind of want. Okay, any questions about ELO rankings? Okay, there are other techniques for coming up with rankings. So one technique that comes out to be common and important is when you have a lot of people with different rankings. So I know you guys, for your assignment, each have a ranking of companies by how interesting they are. Okay? And from last class, I could tell that many of you have different ideas of what interesting means, right? What is the best notion of what's interesting? I don't know. Okay? But suppose I want to use the wisdom of this class. One way that I could do it is if I took everybody's interestingness rankings, I would like to try to combine them into one ranking. Does everybody see that that kind of thing happens fairly often? Okay? Certainly when it comes to thinking about voting, we have an election coming up. In some states, people, there's more than 2 candidates. The voter has to rank all the people that are on the ballot. This is my first choice. This is my second choice. This is my third choice. This ranked preference voting. They use this in Alaska, I know, and in some other states. Okay? Now, how do you combine those answers to get a ranking of a single ranking from this? The basic approach is something called Borda's method, which is to assign a point total for each one of the possible positions. Okay? So here we have a world where there are 5 candidates labeled A through E. We have 4 voters, 1 through 4 voters, 1, 2, 3, and 4. Each column is a voter. They order the people according to their desired rank, from best to worst. How do we find a consensus among the voters? Okay, yeah?
They sign up point values for each position, and whatever position has the highest points usually wins these things. So if you're like first choice vote, you have 5 points.
Okay, so one way to do it, that seems like the natural one, is you assign each person's position in each position a point total. Here, first place was 1 point, second place was 2 points, fifth place was 5 points. You can then, for each candidate, take what was their position times the number of points that they had and sum that up. So A got 3 points for being ranked first 3 times and 2 points for being second on one ballot. That's A's ballot choice. A got 5 points. Okay? D got 3 plus 5 plus 4 plus 4. Hopefully that comes out to be 16 points. Any questions about this? Okay? Does this method seem fair and reasonable? Okay? What are limitations or assumptions in this? This seems like a way of getting a consensus. Does anybody see any implicit things here that could be decisions or something like that? Yeah.
You can have a candidate who has very high and very low ratings, and they be ranked the same as someone who has decent ratings across the board.
Okay, one consequence that this is kind of a linear system, that's true, if half the people think I'm the greatest person on earth and half the people think I'm the devil incarnate, We may or may not have a presidential candidate which strikes that feelings, okay? You would get a middling vote, right? And it's true that that would be the same if you had a bland candidate that nobody really hates but nobody really likes. They would come out to be the same in the system, okay? Any observations here otherwise that you could do? One thing that
Scores could type.
What?
The scores could type.
Sorry about that. Say it again.
There could be any tie in the scores.
There could be you can say a cycle.
Tie. Draw.
Tied scores.
Oh, there certainly could be ties in here, okay? And ties mean that there's equal preference, possibly between the vanilla candidate and the, high variance candidate, okay? So certainly there can be ties. Notice this treats all the voters equally. Do we like that all the voters are treated equally? Maybe in an election we like that. Now in rankings, it could be, what if I knew that some of you were good students and some of you were lousy students? Would there be a way, should I count your votes for what's most interesting equally? Maybe, maybe not. How would I incorporate differences among the voters? Yeah?
You weight the different.
You could conceivably have a weight for each voter. Does everybody see that? Okay, so that I think is and that would solve that problem. The other question here that's maybe more interesting to think about is, should the weights, that you assign for positions be 1 through n, or should there be a different function? Okay, you kind of see that? What are the consequences of making this thing linear? Okay, which is what we did there. One consequence, again, was that the highly variant candidate got the same as the vanilla candidate. Okay? Should these weights be linear? Does anybody have any opinion? Let's say you were going to rank, all the companies. Which companies do you think you're most sure about? There's a difference between, let's say you're ranking the companies by your method, by how interesting they are, right? And interestingness, you have an opinion of one is more interesting than another. If I wanted to say what was your confidence level about where you assigned it, do you think that your confidence level is equal all the way through? Which way do you think your confidence level is?
At the top, you're more confident.
At the top, you're more confident. When I'm assigning grades to you guys, I'm going to see some students stand out at the end. Wow, this person got it. Perfect, perfect, perfect. This guy's really great. Then there's going to be a sea of people, who are all roughly the same, And when there are a sea of people that are roughly the same, I'm not so confident I can discern the differences between them, right? So what's a way to think about weights for this kind of a voting scheme? Linear position weights make sense when we have equal confidence in how accurately we are scoring you at any point in your ranking. In general, that's not really true. I would say most of us have greater confidence in our ability to discern the best or the worst than the ones in the middle. So what's a solution? One solution is to use uniform samples in a normal distribution as the weight. Let's think about what happens with this case. So here, what is the story? You guys recognize that red thing as a normal distribution. We'll talk more about it next class, but I think that much you guys understand. Now, what is this supposed to be, these lines supposed to be? They are supposed to be equally spaced, okay, samples in the normal distribution. Meaning, if we did this right, the area between any two successive points should be the same. The probability mass should be the same between any two of these lines, right? Does everybody see that over here at this point we got this short, relatively fat sector, right? And next to it I've got a taller but thinner sector, right? Can you believe that the area of these two are the same? Hopefully. I have to integrate it, but I believe that that's true. If I did it right, that's true. So what is the idea here? If I looked at the cumulative distribution, let's say I had 100 things. I wanted to rank 100 things. If I look at the cumulative distribution function of the normal distribution and take the sample at 1%, 2%, 3%, 4%, ... I will get the x positions of these blue bars. Does that kind of make sense? Any questions about it? What do we notice? The bars seem much closer in around the center of the distribution. Why is it? There's more mass here. But what is the implication if I use the x values of these bars as my weights for the rank to combine the rankings? The difference between being the median value and the next to median value is going to be a very, very small difference in weight. Does everybody see that? Whereas the difference between being first and second is a much bigger difference in weight. So this one will reward you for being, it'll give you a bigger reward for being at the positive extreme, a bigger penalty for being at the negative extreme. Okay? And a rating scheme like this might make more sense in adjusting these things. Any questions? Yes?
Might a consequence of this be that, say someone was ranked like middle across the board, even though the points being assigned is lower than, say, the person being ranked last across the board, they have such a higher weight that they're going to end up being below that last ranked person.
Wait, no. Suppose you have somebody, notice that these weights, the low-ranked person is getting a negative weight.
Right. Oh, okay. Yeah.
Okay, so this is 0, this is positive weights, these are negative weights. So if you have the dud who is at the bottom of everybody's ranking, they got that times a large negative value. They are going to get a really dumpy score, right? If you're in the middle, well, you're getting a neutral score by this model. Okay? Yes?
One thing I'm wondering, in practice with at least like how voting is in the US, it's more so not the states that are like one end of the spectrum or the other. It's more the swing states that are the deciders. So in this model, it's like those middle ground areas are kind of weighed less.
Okay, so what you're saying is, if you want to take this to the United States, and you're going to say, I'm going to weigh every state according to, let's say, where it ranks in how much it supports one candidate or the other. Now notice that there's a difference. This is about how much am I weighing people. Oh, okay, wait, let's just think about this thing for a second. You're claiming that in this case, you're imagining a problem where every state is independently ranking all the candidates. Okay? These weights are going to be, are these weights, the number of weights going to be the number of states or the number of candidates? No, the number of candidates. Okay? So remember what we're doing here. Go back to this thing here. The number of positions is the number of candidates. Here we had 4 voters. So in our world, we would live in a world where we had 50-odd, 50-odd states voting in your problem. There would probably be something like, between all the weird third-party people, maybe a union of 10 candidates or something like that. And, we would be doing it. Again, using this scheme, what would be the right weight for each? Anyway, yeah, okay, fine. So here, the linear weights probably correspond to like adding the votes, which is kind of what we would want. Okay, but the important thing for what you were seeing is that the weights would be the number of positions, number of candidates, not the number of states. Any other questions about this? Okay. Actually, in ranked choice voting, does anybody know how ranked choice voting works in the United States, in Alaska, or in some other countries, some other places? Actually, they do it a little bit differently. They do something like this. They count who had, they first count who was first in the, how many times each candidate was first. So in this case, A1 was in 3/4 of the time was first, B was 1/4 of the time. Okay? If a candidate actually got above 50%, they say you're the winner, so A would win. But what if, let's say, it wasn't more than 50%? What they then do is they look at which candidate did worst, presumably candidate E, and they then drop candidate E from consideration. And now, more people, there's fewer candidates, somebody's vote total should go up. If you keep dropping candidates to the point where you only have 2 candidates left, either it's going to end in a tie or somebody wins. And that's kind of how the ranked choice methods for voting work. But that's not for here or there. Any questions about this combining rankings system? Okay, good. There's other approaches to constructing rankings, which I think are interesting, which are going to be treating votes in some sense as, we had votes being treated in, in ELO, as being a preference of one over the other, a result of one over the other. If we treated every binary comparison, okay, as an directed edge in a graph, we get a directed graph. Does everybody see it? The vertices are the items being ranked. The edges are pairs of people, pairs of items being ranked. And the direction of the edge said, I am preferred over you. Okay? I beat you in a head-to-head contest. Some voter says I'm better than you. Something like that. Okay? If we have a graph like this, and everybody really agrees deep down on the ranking of how good everybody is, there will be no inconsistencies in this graph. Does everybody see that? And if we have no inconsistencies, there is no directed cycle. If you look over here, we have what looks like a cycle, but that's not a directed cycle. Okay? A directed cycle would mean A prefers B, B prefers C, C prefers A. Okay? If there's no confusion, we get no inconsistencies, no cycles, we get a directed acyclic graph, a DAG. And how would you order the vertices of a DAG? Okay, when you took your algorithms class, yeah? You learned about topological sort. Topological sort is an ordering of the vertices in a graph. So all edges go from left to right, right? Is the topological sort always unique? No, in this case, you could either start with A or G, okay? But it takes any topological ordering. Is consistent with the results of all the comparisons. Any questions about that? Now, in real life, if I ask you a question, ask everybody here to compare pairs of elements. Is everybody going to agree on the underlying order? Probably not. So you have a problem where you have a directed graph where there are cycles, okay? And how can we rank the vertex, order the vertices in a directed graph where there are cycles, okay? This, somehow if we want to use a topological sort or something like that, we have to find which edges we can delete, okay? And the goal should be probably to find the smallest number of edges that are going the wrong way. The best solution would be find the smallest number of inconsistencies such that when we delete those edges, the graph is a DAG, okay? And if so, then we can topologically insort it and all that. That's a good idea. There is a challenge that finding the minimum number of edges to cut from a graph in order to break all cycles is a famous NP-complete problem called feedback arc set, okay? And so there's no fast algorithm to find the smallest number of edges to cut to break all cycles. But there are heuristics and reasonable things you can do to try to delete small numbers of edges from the graph. Any questions about this kind of approach? Yes?
I didn't understand how you choose the edges that you would like to delete. So, is there like a voting system where each edge or each...
Okay, so what would be a good edge to delete? How would you find a good edge to delete? Okay, this is now an optimization problem, okay? I would say it's not obvious to, what would be a good edge to delete, okay? One way to think about it would be, it's hard to look at an edge and say you're a bad edge. So that I don't think is how I would think about it. What I would think about, though, is you're ultimately trying to find an order of the vertices. Do you agree? Can I tell whether one ordering is better than another ordering of the vertices? If I give you a permutation of the vertices and another permutation of the vertices, which one is better? Okay. Suppose I take the vertices of one of these cyclic graphs and I come up with a permutation and ordering of it. Is it hard to count the number of edges that are going the wrong way? No, that's a routine matter, right? Once I have an ordering of the vertices, if I want to compare every edge ij, if I know where in the position of my order vertex I is and vertex j is, I will know whether it did right or wrong. So it should be clear that I can score how good an arrangement is. And now the right thing to do is to find the right ordering of the vertices that has the smallest number of edges going the wrong way. Does that seem right? And so there are various optimization things you can do to try to construct orderings where the number of edges going the wrong way is minimized. What if I construct a random ordering of the vertices? How many edges will be going the wrong way? Does anybody see what I'm talking about now? I have you guys have a preference function. I now just simply come up with a random ordering of the vertices. How many of the edges get cut or going the wrong way? On average, in expectation? Half, right? If I turn the permutation around, all the ones that were cut were not going to, were cut before are now not cut, and vice versa, right? So a random thing will cut half the edges, okay? In general, by using some optimization like maybe sorting them by the difference between input in degree and out degree. A vertex that has a lot of things going into it and few things going out of it probably belongs at the back, right? So that's a heuristic. If you use something like simulated annealing or some other optimization technique, you can come pretty close. Any questions? Now this year I'm hoping not to have the projects graded by peer grading, okay? The students didn't like it, and you know, but what did I do? I had to rank all the papers in here when you guys had only a, what you call it, the reviewers were only going to review 3 papers each. If I asked them to write numbers on them, what do you think about the depth of this paper? Okay, or how good, how high quality is this paper? Give me a number from 0 to 10. Some of you will be honest reviewers, and some of you are going to try to screw your classmates and say, this paper's a 0, so I get a higher grade on average. So I didn't use those numbers. What I did use was, I knew that I gave you everybody 3 papers, and I said rank them from best to worst. This you could do in a reasonable thing. If you rank one paper first, another paper second, another paper third, does everybody see that that's giving 3 implicit edges into this graph? 1 beats 2, 2 beats 3, 1 beats 3. Then I would find the ordering of the vertices that minimize the number of edges that got cut using a heuristic. And this, I think, worked pretty reliably. Any questions? But I don't think it's going to happen to you this year. Okay? Any questions about that? Okay? Fair enough. Let me show you another ranking method that is on graphs that is pretty good. How many people here have heard of PageRank? Okay? How many people have not heard of PageRank? A few people, that's good. PageRank, used to be an unbelievably famous thing because it was the thing that turned Google into a good company, okay? Google was once this crummy little startup, out of the university. Everyone was building search engines at that time. One thing that they noticed was that certain websites were more reliable than others. How do you, if I've got an article that matches, you type a query into a search engine, okay? You type in, God forbid, my name in the search engine. It appears in a lot of places on the web, okay? Anything that had one of my books has my name there. How do you find what is the most relevant thing? Okay? One useful signal was how reliable a site was it. Okay? And what was the notion of a site being reliable? Well, a lot of edges linking to that site. If I have a lot of web pages linking to my web page must be pretty good. So that would be one way to measure the importance of a node in a graph, was what its in degree was. But that was something very easy to cheat. If I wanted to raise, how could I go about raising the in degree of my website? I find a bunch of people whose website doesn't mean very much to them and have them link to me, right? Or I make up a bunch of new websites that sole purpose in life is to link to me. So, but PageRank is a way to kind of analyze a network and try to figure out the importance of which was the most important vertex. In a way that covered up for many, that blocked many of these cheating schemes. What was the idea of PageRank? The PageRank of a vertex in a graph was going to correspond to the probability that a random walk on the graph would end up at a particular vertex. Okay? So if you have an in degree, is it more likely that if I say, you do a random walk and I now say stop, is it more likely somebody ends at a high degree node? Yes, because there's lots of ways to get to me. But it's even more important that those individual things that are linking to me be important also. Okay? If I have 1 million unimportant websites linking to me, that isn't going to get me much traffic in principle. So what is the PageRank function? PageRank, again, is the probability that a random walk ends up at a particular vertex. What is the probability that the probability that you're going to end up at vertex V on the jth step of your random walk? My claim it is, if we sum out of all vertices that go to vertex V, see how the direction goes from U to V? The probability of being at U on the previous step, that's the j minus 1, divided by the outgoing degree of each vertex. If I have a high degree vertex and I'm taking a random walk out of me and I have 100 edges out of me, the probability I go to U is 1 out of 100, right? So does everybody see that what we're doing in each iteration is we're computing the new PageRank in the jth iteration as a function of the PageRank of each vertex in the j minus first iteration. And basically what it's doing is taking the weight, okay, at each node and spreading it equally among all of its descendants. Okay? This constructs a kind of recursive formula, okay? And as it turns out, after a relatively small number of iterations, these probabilities converge. Any questions about that? Does that make sense? Okay. So what's good? Okay. Again, you've heard there's a famous saying that says all roads lead to Rome. Why do all roads lead to Rome? Because it's an important place. It's likely if you took a random walk, you would end up at, there's a pretty good, better chance you'll end up at Rome than at Stony Brook. Okay? PageRank is a very good feature. And when you're dealing with networks, if you want to capture the importance of the vertices or the centrality of the vertices. When I ran, in one study we did, we looked at all the people who were mentioned in Wikipedia, and we computed the PageRank of the network where every page in Wikipedia linked to every other page. So we computed the PageRank of every page on Wikipedia, and then looked at the PageRank of all the people in it to try to figure out who were the most important people in the world. Okay? And when we did this, some of these people you may know. You can guess that we did this study when Obama was president, so that's why Obama looks so famous and you don't see Trump, right? Are there any names on here you don't recognize? Okay. Who has a name they don't recognize? Yeah? Carl Linnaeus. Who was Carl Linnaeus? Does anybody know who Carl Linnaeus was? Someone here knows what Carl Linnaeus was. Have you ever heard of the Linnaean system for classification of animals and wildlife? Who here is a Homo sapien? Raise your hand if you're a Homo sapien. Yeah, okay, hopefully all of you, right? Okay, Linnaeus was the one who classified all of life, okay, into species. Now, why did Linnaeus get such a high PageRank in Wikipedia? Can anybody guess? Yeah? Well, the Linnaean system is used today, that's good. The metric system is used today, and Harry Metric didn't get listed as the, the most important person in history, yeah?
Every species uses that system, so every
plant and animal linked back to Linnaeus's homepage. Does everybody see that? And that's why he was, plants and people. There are a lot of plants and animals. They're pretty important things. You look up, So anyway, when we limited the graph to only being people and computed page ranks, you got, I think, people that everybody knows and would have some idea of who these people were. Okay? So again, when you're doing something like PageRank or anything else, the results you get depend upon what the network you feed it is. Okay? Any questions about that? So what other kind of decisions would go in if you were going to try to use take a network and try to modify it to make things useful? One thing you would like to do is to try to delete any edges or vertices that are kind of to junky places, right? If you know that some website is doing something dirty and you don't trust their opinion, you should delete all the edges from it. That kind of makes sense. Okay? What happens if you have an out degree 0 vertex? Meaning that there is no, that there is no outgoing edge to a vertex, from a vertex. What happens to the page rank of that node? Okay? In some sense, with each iteration, it doesn't have any place to go. Is that right? Even worse, what happened if the only link out from your page went to itself? Saying, this is Skeena's page. Here's how you go to Skeena's page, right? What's going to happen if we try to accumulate page rank now?
All the page ranks, all the rankings will begin into it, so it will become extremely important.
It's going to come, the page rank is going to come into me with each iteration, and it's never going out, right? Eventually, all the world's page rank comes to me, okay? So you need to do something. You better get rid of self loops. You better get rid of loops between, cycles in irrelevant parts of the graph. That's kind of a bad thing. That was a way of cheating. Okay? You want to allow random jumps. When you looked at this thing, one way to avoid these problems is even if I am with a certain probability, I'm going to jump to a random vertex, or I'm going to jump to a vertex they called God that would link to everybody. It's the same thing. And then if you do that, then you avoid these cycles. Okay? Any questions about this? If you have a network, the PageRank is a very good statistic for dealing with that. Any questions? Okay, what is the best possible ranking method? I've shown you a bunch of different methods. There are other methods that are out there. It turns out that there is, in some sense, a proof that there is no best possible ranking method for a ranking system that will always make perfect sense of a set of rankings. And this is something called Arrow's impossibility theorem. And it's kind of said that suppose you're unhappy with the way a country tabulates its votes. Maybe there is a perfect way, a better system than what we do here or any place else. You might like your system to have several properties that feel natural, okay? So suppose you might well want to say that if you are combining a bunch of rankings from people, if everybody likes A better than B, A ends up ranking better than B. That seems like something we would want to have happen naturally. There was some question of whether that was happening if we didn't have negative weights on the borders met, but yeah, so that we want to have happen. We would like the system to be transitive, meaning at the end, if it decides that A is ranked higher than B and B is ranked higher than C, then it should be the case that A is ranked better than C. Okay? That kind of makes sense, something we'd like. We would like our system to always have to give an answer. That for any A and B, either A is better than B, B is better than A, or it's a tie. Okay? We would like it to be a system that's not a dictatorship. One way to come up with a consistent ranking of from all the votes in the class is for me to take the rankings, throw them away, and take my ranking. Does everybody agree? That's a dictatorship. Okay? That will satisfy a lot of these problems, right? Well, if I'm the only voter that's counting, then this thing is here. And we would also like that the preference of whether A ranks higher than B should be independent of any other candidates, right? So you would like to have a system that if you had a third-party candidate here, okay, it's not going to change whether candidate A is better than candidate B. If candidate A was better than B with this candidate, they should have been better off without that candidate. So all of these are kind of natural things, okay? But the natural way that you tabulate votes, this doesn't happen. And let me just give you an example. Suppose we have 3 voters here who are, tabulating, have to decide which of the 3 colors they like best. X likes red more than green, more than blue, right? Y likes blue more than red, more than green. Does everybody see how that's interpreted? Which is the winning color? If we use something like Borda's method, or if you look at this kind of thing, which is the winning color? Does anybody have a feeling how you should interpret this? Yeah? You think it's a tie. Everybody comes in first once, second once, third once. Now, what happens though if we drop candidate blue? Candidate blue drops off of the race. Okay? Is it still going to be a tie among the remaining 2 people? No. What's going to happen? One is going to get 1 vote. Red picks up a new first vote when blue dropped out. And green got that. So I think red would win 2-3, right? This is the kind of paradox that the Arrow's impossibility theorem is saying. Somebody else dropping out changes the relative preference of the candidates. And the theorem goes that there is no ranking system that satisfies all of these properties, which is an argument that there is no single perfect way to do it. That doesn't mean that there's not a useful way for rankings to happen. Any questions? Any questions about rankings? Okay, let me, just for the sake of it, again, when I was thinking most about rankings was when I was trying to identify who were the most historically important people by analyzing Wikipedia. PageRank centrality in Wikipedia was a good measure of importance. But there are other important measures. One would be how many people read your web page. Okay? Who's more important, Taylor Swift or me? Taylor Swift is more important because more people read her web page. Is that right? Who's more important? Whose web page is longer? Whose Wikipedia page is longer? Okay, Taylor Swift or me? I assure you Taylor Swift's, without having looked at it, okay? That, there's a lot more accomplishments. The longer your page is probably makes you a better, a more interesting person. Reflects that you're a more interesting person. You could add a lot of junk to my Wikipedia page. It's not going to make me any more interesting, okay? So what did we do to do the ranking? Well, first, we took these values, and because these distributions were not normal, we mapped them to a normal distribution so that, all the factors were comparable. We used a linear combination of these factors, okay, using a technique called factor analysis, which maybe I'll talk about later, but not now. We ended up correcting for time because we thought that Taylor Swift has a lot of web hits now. How many people are going to be interested in Taylor Swift's web page in 2513? Probably not so much, right? Taylor Swift's great-great-great-great-granddaughter will be at the top of the charts, right? Or something like that. Okay? So, when we did this, we got, satisfying results to me of who were the most historically interesting figures. Okay? And, it did a good job of separating out the people who were famous and well-known and stuff like that. And I found that very satisfying. And once you had these rankings, you could tell, interesting things, okay? How many people here know who was in any recent Nobel Prize winners in physics? Does anybody name anyone who won a Nobel Prize in physics? Yeah? Who? You said not recently, but a long time ago. Einstein won one. Marie Curie won one. They were big shots in those days, right? What is this graph showing me? This is showing me that if you plot the importance, the significance of people, of winners of Nobel Prizes over time, what do you see? Nobel Prizes, in all categories, the Nobel Prizes are going down in importance. Why is it that today's Nobel Prize winners in physics are less important than they used to be, yeah?
Because we know more, so there's less, people are not as interested as they used to be.
It may be that as you learn more about a field, that the, kind of reputation, some of the discoveries you really need to know about were done by the earlier people, right? Why is it that with every prize, it looks like the earliest prizes winners were on average more important than the ones after them? Probably because at the beginning, if you're giving the first Nobel Prize in physics, you have a bunch of famous guys who haven't gotten it yet, right? After a while, you give it to the big cheeses, and now, you're left with less important people. The interesting thing is that the winners of the Nobel Prizes in literature and peace have not been dropping. These people still are kind of as important as they used to be. These kind of are maybe more contemporary subjects, and the lead writer at any time is still an important person. The guy who's winning the Nobel Prize in peace is an important political leader. Any questions about that? And all kinds of other things that you could see when you look at rankings. My favorite other discovery was there are far fewer women in Wikipedia than men, okay? But when you look at the importance level of the people, the women in Wikipedia are better on average than the women in than the men in Wikipedia, okay? Which is a sign that for whatever reason, you should probably put more women into Wikipedia to lower their average quality to the level of men. Any questions about rankings or anything like that?